Welcome to part 2 of the Contact Manager project. In section 2, we are going to learn about the binary search. We'll begin by quickly reviewing the linear search, and then we'll learn about the advantages and limitations of the binary search algorithm. So, let's first discuss the linear search and where it gets its name from. So, the linear search. In a linear search, you have a list with some number of contacts in it. You simply iterate over the list, looking to see if each value in the list is a match for the thing that you're searching for. So why is it called a linear search? You might think it's because you're progressing through the list in a linear fashion, and it certainly might be, but there's a deeper reason as well. And that is that as the number of items in your list increases, the number of iterations it will take to find the last element in the list, or to prove that the element you're searching for is not in the list, will increase at a 1-to-1 ratio. In other words, there is a linear relationship between the size of the list and how long it will take to search the list for the last or non-existent element. And that's what makes the linear search relatively inefficient for large searches. So, is there a better way? Well, oftentimes there is, and the binary search is certainly one of those better ways. It comes with some limitations. Let's start by getting our code set up so that we can implement a binary search. And we're going to do that by copying our linear search code, and then we're going to hollow it out. So we're going to paste a copy in. We're going to change the name of the method to be binary search. We're going to go up here to the line just above where we call our linear search, and now we're going to call our binary search. And then we're going to proceed to hollow out our code, and that's because a binary search doesn't use a for loop. So we're going to leave everything about our reporting here, and remember that we're keeping track of how many iterations it takes for the loop to complete, for the algorithm to complete its job. So we're going to leave that in there, and then we're going to jump and take a look at a graphic demonstration of how a binary search works. So if you hop back to the website here, you'll see that there's a link to the binary search animation. Click on that, and we come to this nice page that allows us to do a binary search where we type in the key value, or the value that we're looking for. It's often referred to as a key value, and we're going to go ahead and type in the value we want to look for. We're going to go ahead and search for the last value in the list so we can see how this compares to a linear search. So these blue numbers here at the top of the bars are the values that we're searching for. The blue numbers at the bottom are the indexes. Now, in the first step of the binary search, the algorithm starts by guessing that the value we want is in the middle of the list. And the center of the list is index element 9, or element at index 9, and it has a value of 10. We compare that to the key value, and that tells us that the value we're searching for is somewhere in the top half of the list. So we set our next iteration so that it will only look at the top half of the list. In other words, we now search through elements 10 to 19. And we once again guess halfway through those remaining elements. That should be element at index 14, I think. So let's hit step, and sure enough. Now notice we've eliminated from contention all of these elements in the bottom half of the list. We've divided the list in half, and we're now only searching the half that's remaining. Now, we compare 20 to the value we found at the halfway mark, 15, and we see that the number we're looking for is still above that number. So we're going to eliminate another bottom half of the list, and we're going to jump to the midway point, which should be 17. And there we go. So, is 20 in, what's the relationship between 20, the value we're looking for, and 18, the value we found? Well, once again, it's at the top half of the list. So now our list is down to just elements 19 and 20. The midway point was 19. So our last attempt is to search for 20. And we found our value. Now, sometimes this can be very fast. What would happen if we happen to be searching for the value 10? Well, let's reset, and then let's step. Well, look at that. It found it on the first try. That's very much akin to a linear search, searching the very first element and finding a match. Okay, what about a value that's not in the list? Well, let's search for 99. What's going to happen? Or actually, no, let's search for negative 99 so we can see it go the other way. So we're going to reset, and we're going to step. Notice we once again start at the halfway mark. Negative 99 is below 10, so we're going to cut our list in half. It's also below 5, so we're going to cut in half again. It's below 2, so we're going to cut in half again. And it's still below 1, so at this point there are no elements left to search. So we reset and start over. All right, so now let's see what happens if we choose an element that is somewhere else in the list. Let's choose 8 because it's one of the more interesting things to search for, because our first guess is going to tell us 9. Or rather, oh no, our first guess told us element 9, which was the value 10. 8 is below 10 in the list, so our next step is going to be the halfway mark. Well, now 8 is above our guess here, so we're now going to eliminate all the elements below the red bar. And our midway point is right here at element 6. Once again, we're going to eliminate the elements below our guess here because 7 is less than the number we're looking for. And we found our guess. Okay, that is how the binary search algorithm works. So how do we put that into code? Well, the first thing that we're going to need is we're going to have to keep track of more than one index. We're going to have to keep track of, if you look at this, notice that our low point and our high point has changed. Where we search in the list keeps getting further and further restricted each time. And so we're going to need 2 indexes to keep track of those points in the list. So our first one is going to be our low index, which is going to be 0. And the second one is going to be our high index, which is going to be equal to contacts.size. Okay, and then we're ready to begin our loop. Now I told you we weren't going to use a for loop. In this case, we're going to use a while loop. And what we're going to say is while our low index is less than or equal to our high index, our loop is going to repeat. What does that mean for us? Well, that means that if our low index ever crosses over and gets bigger than our high index, then the value we were searching for is nowhere to be found, and our search is going to end with failure. Okay, then what are we going to do? Well, just like before, we're going to iterate our iterations counter to keep track of how many times our loop repeats. Okay, and then we're going to figure out what our matching index is going to be for this pass. And we're going to do that by doing a mathematical calculation. We're going to start by taking the high index, and we're going to subtract from it the low index. We're going to take that and we're going to divide it by 2, and then we're going to add back in the low index. Now, what does all of this amount to? This amounts to picking the halfway point between high and low, between low and high indexes. Okay, that's what that mathematical function does, and we'll look at that in more detail very shortly. All right, well, what do we do after that? Well, now we've got an index that we want to see if we found our value. So first, we're going to pick a contact from our list, and we're going to say that that is equal to contacts.get our matching index, and then we want to get the last name first in the form of a string from our list. So we're going to do last first equals a person dot get last name first. And then what we have to do is this tricky bit here. So I have a guess My guess is 10 in this case. I'm looking for 8. 8 falls below 10, so I'm going to eliminate all these elements here. Well, in this case, we're doing an alphabetical list. So how do we find out the relationship between what we're finding, the name we're looking for, and our current name? And thankfully, we have a very special method for doing that, which compares two strings lexicographically, which is a fancy word for alphabetically. So we're going to say our compare result is equal to our last first dot compared to our find string. And if that number is less than 0, then it means that the value is somewhere in the top half of the list. So if I were searching for 20, I would want to eliminate all these values. My next low point would be my midpoint here plus 1. Well, how do I say that? I say first, if compare result is less than 0, then I want my new low index to be equal to my matching index plus 1. Well, what if, as in our example here, my compare result is greater than 0? Meaning that I have found that the value I'm searching for is in the bottom half of the list. Well, in that case, I want to make my new high index equal to my midpoint here minus 1. So I say that my high index is equal to my matching index minus 1. And there's only one possibility left, and that is that they might actually be equal, in which case we've found a match. So we're simply going to break out of the loop. All right. Well, now we have one last problem. Our loop will end if low index is ever greater than high index, or if we found a match. But they mean different things. If the loop ends this way, it means that we didn't find a match. So we can write an if statement to detect that condition. We say if low index is greater than high index, then what we want to do is we want to make the matching index equal to -1, meaning there is no match. And then this is now the code for a binary search. So let's test it by searching for Janowski Milan. And we'll go ahead and we'll restore our window here. And we'll run our code. And here we go. Our linear search took 20 iterations to find Janowski Milan. Our binary search found Janowski Milan in 4 iterations. How's that for fast? That's pretty good. What if the name we were looking for wasn't in the list? Let's change the spelling of the name so it can't be found. Whoops, we have an array index out of bounds error. Let's pause the video for a moment. Okay, it took me a moment to track down the array out of bounds index error, so I made one little typo here. When I was specifying the high index, of course the high index is contacts.size -1, not contacts.size. A little off by 1 error there, caught up the teacher. Okay, so back to our lesson here. What do we get when we run this? Well, if the name is the last name on the list, we got a match after just 5 iterations. What happens if we search for something that's not in the list? So let's just spell their name wrong. Well, we also have no match after only 5 iterations. So how is this working? Well, let's make an attempt here to follow the code. So what we're going to do here is we're going to shrink this window so we can see this little Excel sheet. Okay, and we're going to switch to debug mode. And then we're going to put a stop in right here where we get our result. So this is a breakpoint on the line just before we do our compare here to find out what our result is going to be. And then we're going to run our code in debug mode. All right, so on the first iteration of our loop, what is our low index? Our low index is 0. What is our high index? It is 19. And then we want to do the math calculation to find out where the midpoint is. So let's review how we did that. We started off by saying the midpoint, or matching index, is equal to the low or the high index, 19, minus the low index. We have to divide that by 2 to get the halfway point. And then we have to add the low index back in. Now, because I'm using Excel to do my math here, I'm going to tell it to convert that to an integer to get my result. And my matching index is 9, which matches up with our code here. So what does that mean? Well, since we're searching for Janowski, which is the last name in the list, we know it comes after our current guess, which is going to be, let's see, our contact's last first is Mirror Brock, and Janowski comes after Mirror, so it's going to be in the second half of the list. Well, what is that going to mean for iteration 2? It's going to mean that our new low index is going to be equal to our matching index plus 1. So I'm going to step through the code here, and then we're going to see our low index just changed to be equal to 10, which is equal to our matching index plus 1, and our high index doesn't change. Okay, and then we can continue. I'm going to hit resume, and we'll get back up here for our next iteration. On iteration 2, we have a low index of 10, a high index of 19, and we can calculate our matching index the same way we did before by saying that we want the integer value of the high index 19 minus the low index of 10 divided by 2, and then we add back in the low index of 10. And that is, in fact, 14, which is exactly what our code gave us. Well, who's at spot 14? It's Padveen Connor, and we know that that's interesting. First it says Redding Tanner. Oh, that's right. 14 is Redding Tanner. And we know that Janowski Milan comes after Redding Tanner. So once again, for iteration 3, my low index is going to change. It's going to be equal to my matching index plus 1. So it's going to be 15. My high index does not change. I'm going to go ahead and resume my code here. And now I'm looking at Van Landingham, Brianna, and we could calculate that once again by taking the integer value of the high index minus the low index divided by 2, and then add back in the low index of 15, and that gives us 17, our next matching index. Okay, so what's that going to do? Well, on iteration 4, our low index is now going to be equal to this matching index from the previous step plus 1. So we're going to have 18 and 19 here. And then let's resume and run our loop one more time. And sure enough, we've got 18 and 19. Okay, so let's do our math one more time. We've got our integer value of our high index, 19, minus our low index, 18, divided by 2. Add in our low index one more time. And our next matching index is 18, which means that for iteration 5, our low index is going to be equal to this plus 1. So our low index and our high indexes have just become the same value. So what is that going to mean for the next iteration? Well, what is our matching index going to be? Well, if we do the math, it's going to be 19 minus 19 divided by 2 plus 19 will give us, of course, 19. And who is at index 19? Janowski Milan, which means on this iteration, what is our compare result going to give us? So let's see. Last first. Oh, whoops, we were searching for something that didn't exist, so we got a no matching result. Okay, so you can see that our binary search for Janowski lowercase Milan found no match, and it took 5 iterations. If we followed the exact same procedure for the correct name, we would get an actual match. So what interesting things do we need to know about the binary search? Well, we need to know a few limitations. First, let's go ahead, or some advantages and disadvantages. What is the advantage? Well, if we happen to pick the name that falls right in the middle of the list, that is the equivalent of picking the very first name. So let's search for Mara Brock. What is the fastest that a binary search could complete? Well, if we happen to be searching for the middle value of the list, it takes 1 iteration. That's great. What if we're searching for the value in the list that comes just before that? So let's look for Lou Jesse, and let's see what we get here. Notice that it took 5 iterations to find it. And 5 is actually the maximum number of iterations it could take, and we can prove that by, again, searching for a name that's nowhere in the list. How many iterations does it take to prove that? It takes 5. That is, in fact, the maximum. Why does it take 5? Well, it essentially takes 5. We're going to use Excel here just for a moment to demonstrate, because each time we're taking the number of elements in our list and we're cutting it in half. So, for the first iteration, how many elements remain to be searched in our list? If we started with 20, how many do we have after the first iteration? Well, we have 10 remaining. On the second iteration, how many do we have? We divide that again by half, and we get 5. How many do we have for the next one? We divide that in half, we get 2. Actually, we should round up probably in this case. And in the last one, we divide by 1. And then when we divide our last time, we get 0. Another way to do this would be to say we have 20 to start with, then 10, then 5, then 2, then 1. And when we're down to 1, we either have a match or we don't have a match. Either way, the algorithm ends. So we can figure out what the maximum number of iterations it will take to perform a binary search by dividing the total number of elements in half until we reach 1 or 0, depending upon how you do it. And that is why it is a binary search, because each time it cuts the number in half. So far these all seem like advantages. What is the disadvantage to a binary search? Well, the real disadvantage is that we need a list that is in order. So let's make our list an unsorted list, and then let's once again search for somebody that was in our list. So let's search for somebody that should be easy to find. Mara Brock. Of course, we don't know where Mara Brock is going to be in this list this time, so let's run it. And here we go. That time we got lucky. We found Mara Brock in 3 iterations. Let's try this time searching for Janowski Milan. And let's see how we do. And according to this, Janowski Milan is not in our list. Well, we just verified that, in fact, Janowski Milan is in the list. It's just out of order alphabetically. It's expecting Janowski Milan to be here at the bottom of the list in the Y's, but it's not. It's up here at the top, and so it can't find it. A binary search only works if the data is in either ascending or descending order. And that's very important. And you must know the order. It should match. For example, let's see what happens if we do order descending. Oops. Dot order descending. Okay. And again, it says no match. And that's because our list here is assuming the direction where it is in the list relative to the value that we found by picking the middle item. And we've just now reversed the list so that Janowski is at the top. We could fix this easily enough. If we knew our list is in reverse alphabetical order, all we have to do is change these, and now it will work again. See, it found it in 4 iterations at index 0. However, that requires, again, that we know the order of the list. The list must be sorted in either ascending or descending order, and our binary search algorithm must be written to take advantage of that order. Otherwise, it will fail. And it will fail and not tell you that it failed. It will simply give you an erroneous result. And that is the binary search algorithm.